Okay, so the first thing we're gonna have to do, so this is for drawing Lewis structures, okay? And again, Lewis structures are the 2D version, like the flat version on paper, of covalent compounds, which are all nonmetal. So hydrogen, don't forget hydrogen, and everything on the right side of that staircase on the periodic table. All this stuff over here, plus hydrogen on the left. Okay, so keep that in mind. So the first step, okay, is to count the total number of valence electrons. Count the total number of valence electrons, okay? So the valence electrons, they're the outermost S and P electrons, okay? So outermost S and P electrons. That's known as this valence electrons, okay? So the valence electrons are the outermost S and P electrons. For example, if you look at beryllium, do you remember how beryllium, what did its electron configuration finish with? Beryllium. 2s2. Now, I know beryllium is a metal. We're not going to even, well, actually, beryllium does weirdly show up in some of the Lewis structures. So beryllium finishes with 2s2. Yes, it has 1s2, but it's not the outermost electrons, right? The outermost electrons for beryllium is 2s2. So beryllium has 2 valence electrons. Very, very simply, if you look at the periodic table, the first whole column, the whole first column has 1 valence electron. The second whole column has 2 valence electrons. We're going to skip the transition metals because they're not involved in these covalent compounds. We're going to go straight to boron. Boron is going to be 3, boron's group, right? Boron, aluminum, gallium. They're going to have 3 valence electrons. Carbon's group has 4, nitrogen's group has 5, oxygen's group has 6, fluorine's group has 7, and the noble gases have 8. Okay? So let's take a look at something like this, a very simple covalent compound. How many valence electrons does carbon have? You literally just counting, you just count 1, 2 on the left, skip the middle transition metals, and you go 3, 4, 5, 6, 7, 8 to the noble gases. So what about carbon? 4. Right? Hydrogen's group is 1. The next group, beryllium's group. When I'm talking about group, I'm talking about column, right? So hydrogen's column is 1, beryllium's column is 2, boron's column is 3, carbon is 4. How about hydrogen? 1, right? But because there's 4 hydrogens, you need to multiply by 4 because there's 4 hydrogens. You add this together and you get a total of 8 valence electrons. These valence electrons are what you're now allowed to use to draw your 2D structure. Your Lewis structure is the 2D version of how this molecule will look, where the bonds will be, what's connecting the carbons to the hydrogens, and if there is what's called lone pairs of electrons. Okay? So step 2. Step 2 is pretty much decide the central atom. Decide the central atom. And the central atom tends to be the atom that's by itself. First of all, there's only 1 carbon. So that's a huge sign that carbon is probably the center atom. Not only that, but yeah, for this particular situation, because carbon is solo, it's definitely the central atom. And we'll look at situations where it gets a little confusing on which might be the center, but this one's a clear-cut center, okay? So what you do is you throw carbon in the middle, and you're going to spread out the remaining atoms around carbon. Now, on a 2D model, the furthest you can place the H's is like how I showed you right here. Up, down, left, right. It could be an X, sideways X, but this is as far away the hydrogens can be, and this is true. These atoms, the bonding electrons, so how many, by the way, we had 8 valence, right? 8 valence electrons. Okay. So what we're going to first do is bond the center atom with the external atoms. We're going to bond them. And we're going to bond them first using all single bonds. Okay? So what you're going to do is add a bond here, add a bond here, add a bond here, and add a bond there. Now, I did mention these are covalent compounds. And so what's happening is carbon had 4, remember? Carbon had 4 valence. So carbon has 4 on its outside, and it's looking to hold hands with like another electron. It's 4 electrons that are on the outside of carbon. So if you think about it, let's say it wasn't these lines, right? Let's say carbon had like these 4 electrons like that, like these dots. And hydrogen, how many valence electrons does a single hydrogen have? 1. So there's 1 here, 1 here, 1 here, and 1 here. Do you see how we're adding up to 2 electrons in between each of the carbons and hydrogens? So what happens is this hydrogen says, "Hey, carbon, I know you need I know you need more electrons. Let me share this electron with you. If you can share one with me, because I really want 2." Okay, hydrogen really, 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 really wants 2 electrons. They're happy with 2. Hydrogen is such a small atom. Once they have 2 electrons, they have their shells full, like 1s2, right? And so hydrogen's very happy with 2. On the flip side, there's what's called the octet rule. And the octet rule is that every other atom on the periodic table, every other atom wants 8. Octet rule. They want 8. If they get 8, they're happy. If they don't have 8, they're not happy. Some atoms, though, can break that rule and go beyond octet. But generally speaking, everyone wants 8. Okay, and if they have 8, they're happy. So going back, let's say instead of drawing dots, what you're going to draw is, because, hydrogen's saying, "Hey, I'll give you 1." Carbon's like, "Oh, I have 1. I have actually 4, and there's 4 of you. So I'll give each of you 1." And so what happens is the electrons are going to bond. And when they bond and grasp hands, they make a bond. And the bond is shown as a line. So you're going to draw 4 lines like this. Each line is how many electrons?
I found this on the web.
Each line is 2 electrons, right? Okay, so we have, if you count, right, it's 2, 4, 6, 8. We had 8 for our drawing. We're done. We can't draw any more electrons. If we had electrons left over, we would have to draw them in, and I'll show you that in a second. So let's take a look and just check really quickly if they're all happy. That's the main thing. You just gotta make sure they're all happy, and this would be the correct Lewis structure. So hydrogen. Is this hydrogen here happy? It has 2. Remember, a line is 2. Hydrogen really wants 2 electrons. So this hydrogen's happy, this hydrogen's happy, this hydrogen's happy, this hydrogen's happy. Is the carbon happy? Yeah. Remember, octet rule. All the other atoms want 8. That carbon has 8. This is the right structure for CH4. CH4 is also methane, which is the gas that's coming out, when you're burning a Bunsen burner, and also on your stove at home, that's methane gas, CH4. Okay? All right. Let's try something that doesn't exactly work out in that way. Okay? 1 second. Okay, so why don't you go ahead? Why don't you try, just add up the valence electrons first. What will be the total for this H2O thing? Anyone have a number? Yes. 8? 8. Very good. Y'all okay with this, adding? Hydrogen's 1, right? Always 1 times 2, because there's 2 of them. Oxygen is in, you go 1, 2, and then you jump the transition metals, and you go 3, 4, 5, 6. Oxygen 6, so we got 8 again. Which atom would you like to put in the middle? Oxygen. Great. Okay, there's only 1 oxygen. Let's just throw that in the middle. Okay, and then there's only 2 hydrogens now. Where would you like to put the hydrogens? On either side? Sure. You want them as far as possible. You know why? The VSEPR, okay? VSEPR theory, which is VSEPR, is called valence. VSEPR. It's called valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. And this theory states that electrons, what charge are electrons, by the way? They're negatively charged, right? And remember what I said about even the orbitals? They don't want to be in the same box, do they? If they're allowed, like Hund's rule, right? Hund said, if you're allowed, you have to throw them up in separate boxes before you have to force them to be in the same room. Okay, you got to go up separate boxes. So electrons don't want to be near each other. They repel each other because they have similar charges. Negative charges with a negative charge is like a north pole and a north pole of a magnet. They repel. Okay? So let's continue. Where should I first use a bond? You're going to first connect, okay, central atom to the outer atoms with a line. That line represents 2 electrons. So out of the 8, how many have I used right now? 4. I have 4 left. Anytime you have electrons left over, first of all, do you see how the hydrogens are happy? The hydrogens are both happy right now. Anytime you see one line to a hydrogen, you're done. That hydrogen cannot get any more. It cannot have another line on it. It can't have a dot on it. It's over, okay? So anytime a hydrogen has a line, you leave it alone, okay? The only thing left now for the 4 to go is the oxygen. And that makes sense because the oxygen's not happy right now. How many does oxygen want? 8. But right now it only has 4. So the 4 left, you're placing them as what's called lone pairs. They're a lone pair because they're not used for bonding. So if you're not bonding, you're lone, right? You're lonely. So lone pairs, okay? The 4 go here. So you're gonna put the lone pair here, 2 here, and 2 here. Now, as of right now, this is what you know water to be. But this is not going to be the final case, okay? You're going to find very soon, like maybe tomorrow, that water should look more like this. It's called a bent shape, and the lone pairs like this. it's still very similar, but we know that anytime a situation arises like this that I've drawn here, this structure is going to bend. It's going to be called a bent shape, and you're going to bend it with the lone pairs that way. Now, this is a 2D drawing, so I still haven't really shown you exactly where these lone pairs go. But if you can see, I'll show you tomorrow, okay, how structures actually blow out 3D. This is just 2D, so you're drawing it like this, but if you had a 3D world where you can pop out of the page and into the page, how the structure would look, it would look a little bit different. Like these two would be popping out at you and above, like popping toward you and above, and then these two would be shooting into the screen toward the back and up, and then these would go back and up, and these would go toward you, okay, toward you and up, if you can imagine that. And have H and H just straight up flat on the page, left and right, diagonal here and diagonal here. But these are back and up, and those are toward you and up. Okay, so let's continue on. Let's try this one. This one has a charge, NO3 with a -1 charge. So this one kind of throws it off a little bit. What do you do with the charge? Yeah, exactly. This charge you need to add as part of a valence electron. So if you have a -2 charge, you have to add 2. If you have a -3 charge, you add 3 to the total valence electrons. Got it? Remember, when you have a negative charge, that means you have one more electron than you're supposed to have. You have one more, or 2 more, or 3 more, depending on... And on the flip side, what if it was a +1 charge? If it's a +1 charge, you have one less electron. So you have to subtract an electron from the total. Okay? So let's do the total really quick. Nitrogen has 5. Oxygen has 6. Again, if you're looking at the periodic table, and I'm just doing this to make sure people are following, this is what I mean. This whole column has 1, this whole column has 2, and then you're just counting 3, 4, 5, 6, 7, 8, and this is the noble gases, okay? Right? So you're just adding like that. So nitrogen is in the 5th column, so it's, right, 5. Oxygen is 6 times 3 plus 1. This negative charge means you have to add 1. So then what do you have? You have 24 total. 24 total. Okay, now let's throw nitrogen in the middle. This is the first time we've had 3 atoms now, or we had 4 already, but like surrounding it. How do you want to space out the 3 oxygens? A T? A triangle, right? Triangle is the best way, right? As of right now, even if you did this, it's totally okay because we're doing just a flat, simple Lewis structure. We're gonna then change the Lewis structure into a 3-dimensional structure, and we're gonna be looking at that a lot more using models. We have like ball and stick models that you're gonna be dealing with. We're gonna use like marshmallows and toothpicks to kind of see things like that. We have oxygen, 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 so we'll spread it out like that. And then what's next? Single bond, single bond, single bond, yeah? So 24 minus 6, okay? This means that I have 18 left. I have 18 left. And what should I do with the 18? Okay, so this next step, right? When you reach this step, anytime you reach this step, what you do is you start putting lone pairs on the outer atoms until everyone's happy. You're trying to make everyone happy. So start with the outside atoms first. Oxygen. How many does this want? It wants 8. How many does it have? It has 2 right now, right? It has 2 from that line. Okay, so the oxygen here has 2, 4, 6. Notice how I placed the lone pairs also. I placed them opposite of the line, diagonally opposite, straight across opposite, and then on the side. Even these want to be the heck away from each other. You know what I mean? You got to spread them out as far as possible. And on a 2D surface, the best way you can do is show like a plus sign or a cross or an X, however way you want to view that, okay? How about this oxygen? Same thing, right? 2, 4, 6. 2, 4, 6. How many green dots or lone pairs of electrons? Lone pair, this is called a lone pair, okay? That's one lone pair. But how many electrons did I draw here? Total. 18. So I'm done, right? 18. I had 18. I'm done with 18. The last thing you need to do is to make sure that they're all happy. That's the big thing. Are they all happy? Is the question. There's something wrong with this drawing. So if you're gonna look, this oxygen is happy, right? This one's happy. This one's happy. But what's wrong with this one? Yeah, right? It's not happy. So this is a problem. Major problem. So this is not the correct structure. Now, when you're unhappy, this is the thing I follow. Missing 2. How many are we missing? We need 2 here, right? If we had 2, everyone's happy, right? If we had 2 more. So missing 2, then probably you have 1 double bond. When you make a double bond, when you make a single double bond, you actually make up 2 electrons. You gain 2 more when you make a double bond. So in a case when you're missing 2, you probably have 1 double bond. That'll make up 2 electrons. If you're missing 4, you can have 2 double bonds. You can have 2 double bonds or maybe 1 triple bond. A triple bond is like adding 2 more lines, right? 2 double bonds is adding 2 more lines. So every extra line you draw, you're making up 2 electrons. So it's either 2 double bonds or 1 triple bond, and it'll depend on the structure. So in this case, I'm missing 2, which means that I have probably 1 double bond. And if you were going to draw this, it would be like this, and a double bond. You start from scratch. What was the total number again? 24. Now, in this case, I drew 4 lines. So how many is that? That's minus 8. I have 16 left. I'm going to draw dots until I hope everyone's happy. So 2, 4, 6. The oxygen at the top only needs 6. This oxygen also needs 6. But this oxygen, because it has 2 lines now, that's already 4, it only needs 4 more. So you're going to put them like a triangle. Like if it's here, then it's here, then it's here. Like as far away from as possible. So I place the electrons like that. We've done it. If you look at every single atom now, they're happy. They all have 8. And this is the correct structure for nitrate. Now, when you draw nitrate, remember nitrate, what did it have? It had a charge. Anytime a structure has a charge, you need to draw brackets around the final structure and put the charge outside. You have to put brackets around the structure and put the charge outside. Okay? Now, it goes a little bit beyond this. Why did I choose to put a double bond here? Why not here? Or here? What made me want to go to the bottom left? I don't get to do that. You don't get to just choose, I feel like bottom left today, so I'm gonna just put the double bond there. It was completely arbitrary, and so it's not correct. The best way to draw this structure, it doesn't end here. There's 2 ways, and I'm going to show you. You actually need to, technically, if you were going to do this correctly, you need to draw the double bond in every single position, all at the same time. So you're going to have one that looks like this with a double bond at the top. And you're going to have a third drawing, right? Because there's like 3 possibilities, yeah? So you're going to have a third drawing with the double bond on the bottom right. Don't forget the brackets with the charge outside. This right here is known as these structures are known as a resonance structure. Resonance structure. Resonance structure. Okay? Resonance structure. In truth, okay, all 3 of these are correct. And if you can superimpose all 3 of these on top of each other, you see nitrogen is not. Here's the thing. The double bond isn't sometimes on the bottom left. It's not sometimes at the top. It's not sometimes at the bottom right. It's actually all 3 of these structures happening at the same time as a resonance structure. All 3 are happening at the same time. So a third way you can draw this technically is drawing little dashes for each of those. Each of those. So it's really like, and all molecules are going to be very symmetrical. So all of these bonds that the nitrogen has with oxygen, they're the same length. Because single bonds are the longest bonds. Single bonds are the longest bonds. Double bonds are shorter but stronger. And triple bonds are even shorter and stronger. It's like if you were holding hands with someone, right? As a bond, right? You're holding hands. If you're using one hand, it's kind of strong, but you can also stretch very long, right? What if you had to have what if you were holding hands with someone with 2 hands? You're going to be closer, right? You're going to, like, one hand you can kind of spread out like this, stretch out. But 2 hands, now you're holding 2 hands, you're going to be closer, and the bond is even stronger, right? If somebody tried to break that by running through it, it would be harder to run through 2 hands, right? And then even 3 hands holding together would be even shorter of like closer together and even stronger still. Okay? So what this particular structure is doing is each of these is in between a single and a double bond. It's almost like right in between a single and a double bond. They're all the same length. They're all symmetrical. And this is the proper structure for nitrate ion. You can draw it like this, or you can draw it like how we had it before a second ago. The 3 structures with the double arrow showing the double bond in 3 different places. All right. One last one, and then we'll see if you can practice a little bit, and then we'll practice like all day tomorrow, okay? In class, we're just gonna practice. SF6. Check it out. Where is sulfur in the scheme of electron configuration? Do you see how sulfur is in the 3rd energy level? It's 3p, right? Sulfur is 3p4. Now, any central atom that is in the 3rd energy level and below, any central atom that is in the 3rd energy level and below can violate the octet rule. They can actually have more than 8 surrounding them, and it's okay. So you can, if forced to do so, sulfur, because it's in the 3rd energy level, it can actually carry more than 8 valence electrons around it. The reason being is that the 3rd energy level also has the 3d orbitals. The 3d orbitals are like spillover. So if sulfur needs to take in more than 8 electrons in its outer shell, it can do so because the 3d orbitals are very nearby. You know how the d orbitals start at 3d? So the 3rd energy and below, they can do it. So let's just do this with SF6 really quick. Sulfur, let's count the total valence electrons. 6 plus 7 times 6, 48. We're going to add sulfur smack in the middle. 6 fluorines. I want you to think of it as straight up and straight down. You don't have to. You just have to spread them out evenly. But it's best to do it this way because later on when we start seeing things 3D, I want you to always think of something going straight up, straight down, and then everything else in a middle, in a center plane. So F there and F here. Okay, so straight up, straight down, this, and this. Now, I don't know if I want to draw this right now, but maybe I will just so I can show you. This middle plane here is flat. Think of it as this plane here like this. Let me draw you like a pyramid going upwards. Do you see that? Oh, whoops. You literally don't see it. Do you see that pyramid that I've kind of drawn upward toward a point from the 4 fluorines that are in the middle plane? It's four-sided pyramid going upward. So the 4 fluorines are here and 1 fluorine straight up top. So 4 fluorines here in this middle plane and 1 fluorine straight up. Each of those, if I drew a dotted line toward it so you can see like a 4-sided pyramid, there's also a 4-sided pyramid going down to this point, you know? Don't worry about it. You don't have to see it right now. Just know that you have sulfur in the middle and 6 fluorines around it with a line, okay? All right. So how many electrons did I use? Out of the 48, how many lines did I draw? 6. How many electrons is that? 12. How many do I have left? 36. So what I can do is I can place these 36. How many does each fluorine still want? It wants 8 total, right? It has 2, so you're gonna put 2 here, 2 here, and 2 here. 2 here, 2 here, 2 here. You know, there's 6 fluorines, right? So that's 6 times 6, that's 36. Isn't that perfect? That's exactly how much we have left. So now all 6 fluorines are happy. The sulfur is happy. I know it has more than 8, but that's okay because sulfur is allowed more than 8 because it's in the 3rd energy level. Not only the 3rd energy level works, 4th energy level works, 5th energy level works, 6th, 3rd energy level and below, right? So bromine, can bromine get more than 8? Bromine is below sulfur, so yes, bromine can get more than 8. Can iodine? Yes. Anything, can chlorine? Yes. Anywhere in the 3p, the 3p, 4p, 5p block, they can have more than 8. Okay? Okay, so what I'm going to have you do is open up your worksheet, and why don't you just try a few of them on the first page. There's a lot more to go, but we're going to stop there, and then we will continue tomorrow, okay? A lot of practice tomorrow, a lot of practice this whole week. And then you're going to have that wonderful spring break, and then right when you get back, we're just going to review, and then we're going to do a bunch of labs on this stuff, okay? All right.